Continuing on with class number 4, and we're talking about gear trains. And here was from another figure from a book by a gentleman named Robert Norton, just demonstrating another gear stages right here. Now, I think it would be good at this point to just take a look at a couple of gears trains. So here is one that I've made, 3D printed, and let's see if we can get that in there all the way. Okay, so the idea here is, let's say that this is the input shaft, right? So I have a little crank right here, and these are 40 teeth. I counted them this morning. I couldn't remember how many I made. I think originally this had a pitch of 10, but because my 3D printer had a limit to how large I could print out this shaft right here, I had to reduce this all by 75%, so it doesn't end up having an exact correct pitch right here. But as you can see, as I turn this crank right here, it's coming. I'm turning this, which for me is coming looking that way, is clockwise, right? That it's turning this one counterclockwise, right? And my finger would get stuck in there. And this is on a common shaft, so this is an intermediate stage right here, right? And so this one drives that one, and then this one drives this one. And so this is the output stage right here. There's various features that maybe I want to point out as we do some more things, like as we go further. I don't have them inside here, but there's always a keyway is necessary right in there, and so that's how I've represented the keyway. I actually was going to print them out, but it ended up being so very tiny and small right there that they're just kind of a pain to go in there. But just there's a kind of sort of enough friction that as long as you don't put too much torque on here, you're going to be fine. So this is each one of these stages. This is 40 teeth, and this is 60 teeth, and this is 40 teeth and 60 teeth. So the center to center distance, as I described at the end of the previous video, works out because this plus this is equal to this plus this, right? It's a simple design, nice and easy, because then I could just print out two of the same gears for each of them. This comes out to a gear ratio of 0.444444. So I'm trying to think of how should I do? How do I get an integer out of that, right? What would I multiply by that to get it to be some type of integer? I guess I could do it right there. So I guess if I turn this one 2.25 times, this thing will turn once, right? So it also works the other way, right? That if I turn this guy right here, this one goes very, very fast, right? So this one makes it slower, right? So let me see here, I'll go. You can't quite see this. I almost wish this was just a little taller. Just a little taller. Can I go up a little higher? Just a little higher so you can see the input and the output at the same time. So let's see. This one is, I'm going to start, this one is at the top right there, right? So I'm going to turn this one let's see, they're both at the top, right? That's at the top, and that's at the top. Great. I could just like, keep, here we go. At the top. So I turn this one time, and it didn't quite make it all the way to the bottom, right? It's not quite. So I'll turn this another time, and it didn't quite make it to the top. So I'm saying if I turn this one more quarter turn, it made it to the top. So there you go. There's our ratio right there, right? Because if I took the inverse, let's see, I'll reverse that back up there. If I take the inverse, I'm hitting the inverse button right there. The inverse of 0.444 is 2.25. So I have that 1 to 2.25 ratio. Or if I go this way, I go 2.25 to 1 ratio is the idea. So it becomes a speed increaser when I go this direction. It's a speed reducer if I go this as the input. So there's a lot of interesting things going on there. We could have, and my background in marine engineering, our gears are often will look a reduction gear so we actually can have two inputs of this. We on old steamships we had a high pressure turbine, and the steam would go through the different stages of the high pressure turbine, and then they would go across a connector pipe where we could take off bleed steam for things, and it would go that would be intermediate bleed steam, and then it would go to a low pressure turbine, which is much larger turbine, and it go through the stages of there, and they ran at different speeds to each other, right? So they would actually have different gear ratios, right? They have two inputs, and they would combine on together to this one main gear, right? To be able to drive the shaft, because on a large ship the shaft RPM is going to be pretty low. It's usually below 100 RPM, whereas this would be like in the thousands of RPM, and the low pressure turbines like going a little bit slower than the high pressure turbine. Maybe not a little, it's a significant amount, but anyway, that's the means by which, so you could actually have two inputs and have another output. Another thing I think that's important to recognize is that some gears only they cancel out, like I should have mentioned in the previous class, or the previous thing, that you'll notice that N3 cancels out right here. So what this in effect is this gear didn't matter. All it achieved was to reverse the direction, right? So now so if we were just coming out to that stage right there, it wouldn't have done anything. The only important would be this number of teeth here at 2 and the number of teeth at 4 would have decided what the reduction was. But what it would done, it would make the rotation of 2 and rotation of 4 be the same. It would also change the distance that the shafts were away from each other. So that's one of the ideas between an idler gear, that it doesn't matter. Like, okay, so they're calling, so you can see that for this, A, let's say, is driving B, right? So number of teeth, right? But then B is driving C. So you'll see that in terms of a gear train ratio, the number of teeth didn't matter in B, and that one of the reasons why it's called an idler gear. It was idle. It didn't really do anything, but it did help us to change the direction, and it did get these shafts further apart, which is often something that we want to achieve just by the arrangement. On a ship, the location of the propeller shaft is offset because the narrowness of the ship as we're coming down, as you're getting further and further aft, getting to the back of the ship starts to get very slender. And so the output shaft is down here, but the actual engines need to be up higher because the ship is too narrow to have them down on the same line as the main propeller shaft. So having that offset, we can it is really beneficial, right? So we might have like something like this right here, where here's the propeller right there, but we have like the main the engines up here, and they have an output, so they'll have a reduction gear that's placed right in there. So you can almost think of it like being a Z that's necessary, just because if you were to take a look at the ship, it kind of has like that shape where there's the propeller is on that level right here, but the engines need to be up higher because they can't fit down in the narrow part of the ship. These are kind of like design constraints, not just for a ship, but for just for many different applications that you're going to have when you're trying to design something just in general. There's going to be some physical constraints that are going to factor in to the decisions that you make. Now, this was an automobile, a manual transmission, and I have a pretty cool little demo little unit. I wish I got to get it fixed because this crank is terrible, and it's like stripped right in there. So I want to make this a pass around, but immediately someone like it just turns and you couldn't get the thing in there. I even flattened off a little side over here, but I think it's the threads of this little screw right here have been stripped, and it just won't tighten up enough. So I was gonna maybe give it to Jonathan Shapiro because I'm kind of tired. I don't have the time to mess around with the thing. But it's kind of cool. The idea here is in the manual transmission is that I can change the path that the thing goes on by taking this gear level low. And it is tough to move this right here. This is why you strip gears when you hear people grinding gears. Let's see. Let's move that to right there. Okay. So let's see. I'll take this gear out of there, and boy, it's not really wanting to move on me. There you go. All right. So let's say that this is. Let's call this first gear. Right there. Okay. First gear is this blue one mated with this yellow one down here in the bottom, and I'm trying to get these things. There you go. There's like a little synchro little piece that helps to guide these gears into alignment with each other. When you put the clutch in, right, you're kind of like you disengage the driving of the thing, but then you're able to like it's able to shift smoothly to get the gears to mesh with each other. You can see that they're sliding away from each other. But anyway, let's see if I can get this thing to turn. No, jeez. This thing really needs to be lubed up. Huh? So that's why the thing doesn't. Yeah. It's easier just to me to turn the output right here, right? So I'm turning this from this is the path that the thing is taking right through there to get to the output. Now, if you disengage and you get to press the clutch in, and there you go. We're able to get now we have that gear and that gear, and these in this case these are the same size. So the input and the output would be going the same speed, but just opposite directions, right? They're just the same speed. It's much more interesting if if I could get this thing and hand it around and get it working well. And now you could also shift it over here. So now, if I can get it engaged, okay, right? Kind of like wiggle it in place. There you go. All right. Now, what's going to happen as part of this right here is the oh man, mine is not sounding good. I gotta get this thing all fixed up. I'm gonna bring it down to Jonathan and see if he can toy with it. But yeah, it's really kind of hung up. But anyway, this smaller gear is driving this. So there's actually let me see if I'm going to say this the right way. Okay, so if this is the input, which it should be, right? If this is the input, this smaller one right here is going to reduce. The shaft is going to go down slower. So that's probably considered that to be first gear. And then maybe we're going to call this next one, if we can get it engaged, second gear, right? So now you can see that this one and these are connected to each other. And then if we shift it, we'll call that, maybe that's third gear, right? Because now this one will make that one go faster, right? This other one, when that red ones were engaged, the shafts were going the same speed. And then lastly, you can see we have an extra gear down here, right? And so what that's going to do is going to be the idler. So that's actually going to reverse the direction. So that's our reverse, right? Is that we've added an idler in there, and now the two shafts are well, actually they're operating in the same direction, but all the other ones, the input and the output were the opposite. So that's like the idea of a standard transmission. and I have like, and there's also these other these little synchro things that we also can bring up. So let's take a look at, let's see. Well, here's my little gearbox that's downstairs. It's like my model of the gearbox. Ooh, there's the idler. Ooh, checking that thing out right there. Although it looks like the teeth are going off each other. Here's a whole bunch of idlers going on, and so a lot of some of the purpose is just to change the direction and to keep these shafts apart from each other. Here's like some of those synchros that I was referring to right here, that and have this like shifting fork that helps to move the gears. You know, like where mine it was really. This thing right here that I'm sliding back and forth is kind of acting like this shifting fork. And you can see how difficult it was for me to get the gear teeth to engage with each other. And don't quote me on this, but I think a helical gear probably has a little bit of an easier time engaging with another gear. But there's this also this little sliding action thing right here. That helps to like smooth the thing in. It helps to kind of make it kind of twist it in a little bit. It's kind of understandable why you hear people grind gears, but they've improved the technology over time to be able to make it so it's not as likely to grind gears when changing them in. But this is supposed to be an animation there where they're showing first, second, third, fourth, and reverse right there. So you can kind of see where these were. And you can even, I think when you go to the purple one, that's going to be this guy right here, which you can see that some of these actually and make the things engage. So let's see, which one was that? Let's see, that was second gear. Yeah, you had to take some time to analyze. That was third gear, fourth gear. And are they going to do reverse? No, they just did first gear, second gear, third gear. You can see that some of these things, some of these actually couple shafts together, like and decouple, right? So. Some of the shafts. So anyway, this is sort of analyzing this is pretty kind of interesting type of thing. So let me go to an example here. I'll pause here because I probably have enough time here. I got 17 minutes in here. So we're going to make a new video.